I'm transitioning the rock videos from year 8 to year 11, 12 chemistry now. So it may be 3 years in between that. So in year 8, we looked at densities, and the reason why the only minerals you're really going to see are quartz and feldspars is because they are lighter, and these heavier minerals sink and don't solidify and remelt. So we're going to talk about these, and we're going to talk about periodic table trends. So there's thousands of minerals, and pretty much all of them are these silicates. So the non-silicate minerals are over here for reference, and the silicate minerals are here. And we're going to talk about these ones, and we'll touch on these too. The clays also just for reference. And so these are the periodic table trends. So what we looked at in year 8 was density. So these ones at the bottom are more dense and they'll sink, especially the iron. Some of these minerals are quite rare, so they won't exist in magma. And some of these other ones are more common. So we have other year 11 and 12 chemistry concepts we need to touch on to understand the rest of rocks, like the three-dimensional and forming and the weathering and stuff. But right now we're just looking at the relation of the periodic trends to minerals. The most common mineral are the feldspars, and we'll talk about why we don't see them because they weather, and that's why we get all the clay minerals. But we're going to just look at the two major types. So potassium feldspar is orthoclase, it's over here, and sodium feldspar is plagioclase. Sodium plagioclase, and that one's not very common. The calcium's not very common. And so what you can see from the periodic table is that they are both similar densities. They're right, that's a little bit more, and they are the exact same ionic charge and very similar sizes. So that's too heavy and it'll sink, and lithium's quite rare, and we're not going to go to 2+. So you're left with these two metals that are the most similar to each other, and so that's the explanation why they can interchange out and replace each other, these little orange dots over here. And it's very rare that you would get just pure one or the other, and you can see from this diagram over here, the mineralogists have determined what percentage. So it'd be like 100, and this here would be like a 50-50%. So the mineral is 50% sodium, 50% potassium. And why is that? That's because they are sort of interchangeable minerals based on their ionic size and their charge. Now, the second most common mineral are quartzes, and quartzes form all sorts of inclusions, but they don't do it very well. And so what you're going to see here is a very large piece of quartz, and it doesn't have anything that's noticeable, no nice minerals inside it. The inclusions that you see are usually, they just usually pop out of a source rock. They don't normally form within each other. And so what you're going to see here is maybe some colored quartz. So that's usually just like the amethyst here. That's only like 50 parts per million, and that's iron 4+. And so that iron 4+ would match a silicon 4+, and that's only a small amount. When you get larger pieces, it just messes things up, such as rose quartz actually inclusions, and it doesn't even form a crystal anymore. So you'll never see a quartz crystal that's pink. Have a look at it, it's been cut. So it's a piece of quartz that's been cut to make look like it's formed a crystal. And so what's surprising here is this rutile. Now, I'm a bit too impatient I have ordered this actual piece, but I'm a bit too impatient to wait, and I wouldn't bring it to school anyway because it's too rare. And that thing cost me $50, and it's tiny. So it'd be good to have like $10,000 to get a nicer piece. You can Google the amazing pieces. And what's unusual about that is there's a perfect crystal formation for both. So the quartz crystal is still a perfect formation, and the titanium, the dioxide rutile, so that's a polymorph. It can form 3 different types of crystals, 3 different shapes. And the rutile form that nice golden crystal is perfectly formed. And so that doesn't make any sense because quartz doesn't form nice inclusions. They're messy, they're dirty, they destroy the crystal. And so if you have a look at the periodic table, you'll see that they are almost the exact same size, very similar densities, and they're the exact same ionic charge. And so that is unique. There's nothing else nearby it except for geranium, which is probably another crystal on its own, but just rarer. And so that explains why the quartz doesn't recognize that that is not a silicon dioxide. And it just keeps, so the rutile would form first and then be fragile and break and get destroyed. But then the quartz forms over it to preserve it, and doesn't get disrupted. It doesn't realize that the silicon dioxide, the titanium dioxide, is not silicon dioxide. And so that's how you get that amazing formation that doesn't occur with anything else. There would be some other instances, but they would be the same reason, similar ionic size, charge, and density. And just lastly, for interest, this is one of the common minerals, not as common as the quartz and feldspars, but the muscovite and biotite. So the biotite's the black, the muscovite's the white. They both have similar properties, except for one's white and one's dark. They both flake, and they all have a similar similar size, but we have different charges for this one. And so you look at the aluminium's 3+, but the magnesium and iron are only 2. But if you look at the numbers there, aluminium's 2, so that's a total of 3+ charge, and the magnesium ion, either magnesium or iron, could be a combination of any of those. They can mix up. All right, they don't have to be all of one or all of the other. So that's 2+ times 3 is 6 if it's all magnesium or if it's all iron. Okay, and so they have a similar charge based on increasing or decreasing the numbers, so the overall charge is the same. Okay, so that shows you why you need to understand periodic table trends to understand one part of minerals.